Okay, so welcome to this next video in which we are discussing group homomorphisms. Okay, right. So in this video what we're now going to do is study another really important concept which relates to group homomorphisms, namely the concept of the kernel of a homomorphism. Okay, now just before we begin our study of the kernel of a homomorphism, let me just remind you of what I said right at the beginning of this video. Okay, and it particularly applies to what we're about to do now. Some of the definitions that I'm about to show you may seem a little bit unmotivated. You might not understand what use they're actually going to be, where this is all going. Okay, but I assure you that everything we do is not trivial. Okay, it will all fit into building us the bigger picture of what a group homomorphism actually is. Okay, and they will all come together and you will get a full understanding of this when we study quotient groups and we get to the first isomorphism theorem. Okay, so for now, just go with it, understand the proofs that I'm going to go through, okay, and just take the definitions as they come, and don't feel guilty or annoyed when you don't actually understand the motivation behind some of the definitions, okay? So particularly when we go on to the definition of a normal subgroup. When you first see that for the first time, it's like, why should I care? Okay, but you will understand why they are so important in future videos, okay? But for now, we're just beginning to gain little nuggets of understanding about group homomorphisms. Okay, right, so let's begin then with the kernel of a homomorphism. Okay, so this is written ker of phi. Okay, the kernel of the homomorphism phi, and in full, kernel is written like so, kernel. Okay, so what is the definition then of the kernel of a homomorphism? Well, the kernel of a homomorphism is basically a subset of the domain group, capital G. Okay, so once again, I'll draw out this familiar picture we've got here. So here is our domain group, capital G, and we'll have our codomain group over here, capital G prime, and we'll now assume that our homomorphism phi is a surjective homomorphism, and therefore that really the only reason that this homomorphism can fail to be an isomorphism is that the mapping is not injective. Okay, so multiple elements in the domain group are being mapped onto the same element in the codomain group. Okay, and once again I'll just color code my two groups. So we'll have our domain group here in red, and we'll have our codomain group here in green. Okay, right. So here comes the definition of the kernel of a homomorphism. This is a subset of the domain group. Okay, so we'll have it here. Here is our subset of the domain group, which is going to be the kernel of the homomorphism. So I'll just color that in. So this little portion here in blue is going to represent the kernel of the homomorphism, and it's the set of all things that are in the domain group, so all little g that are in the domain groups, and that makes sense, such that phi of little g is equal to the identity in the codomain group, capital G prime. Okay, so what this says is it's all elements of the domain group which are mapped onto, by the homomorphism phi, the identity element in the codomain group over here. So all of the elements in the kernel of the homomorphism are going to be mapped onto this one element, which is the identity element in capital G prime. Now, if our homomorphism is injective, okay, then of course, since we've assumed that it is surjective as well, it will be bijective, and therefore it will be an isomorphism. In that case, the only element that is actually going to be mapped onto the identity in capital G prime will be the identity in capital G. Okay, so we've shown that for all homomorphisms, whether they're bijective or not, the identity in the domain group is always mapped onto the identity in the codomain group. So this is always an element of the kernel of the homomorphism. So the identity of G is always an element of the kernel of the homomorphism. And if this mapping is a bijective map, i.e. if phi is a isomorphism, okay, then this will be the only element in the kernel of the homomorphism. So the kernel of the homomorphism will be a very small set. However, if the homomorphism phi is not bijective, okay, then since we've assumed it's surjective, that means it's not injective. That's the only way it can fail to be bijective then, okay? That will then mean that there are more elements in the domain group here being mapped onto the identity in the codomain group. So that will mean that the kernel of the homomorphism is bigger, basically. It will contain elements other than just the identity of the domain group. But the identity of the domain group will absolutely always be within the kernel of the homomorphism. So there is at least one element that always has to be in the kernel of the homomorphism, because as we've shown, that is always mapped onto the identity in the codomain group. Okay, right. So that's what the kernel of a homomorphism actually is. So what do I want to now show about the kernel of a homomorphism? Okay, well what I want to show is that the kernel of a homomorphism is actually a subgroup of the domain group. Okay, so it's a subgroup of the domain group. So this is not just some arbitrary subset, it is actually a very special subset that forms a subgroup. Okay, so we've already done this once for the image of a homomorphism, so we know the protocol for showing that a subset is indeed a subgroup. Okay, we need to show that it's closed, we need to show that it has the identity in, and we need to show that inverses are present in that subset. We don't need to worry about the second axiom of group theory, associativity, because we get that for free. Okay, as soon as it's a subset with the inherited composition law on it, associativity is there. Okay, right. So axiom number 1 then, closure. Okay, so we need to show that if we take any two arbitrary elements, let's say little a and little b, which are in the kernel of the homomorphism, okay, we need to show, so this is to show, we need to show that they're two of them composed together, A composed with B, is also an element of the kernel of the homomorphism. So we've just taken two arbitrary elements of the kernel of the homomorphism, and if this kernel of the homomorphism is going to be closed under composition, then those two things composed together has to be another element in the kernel of the homomorphism. That's what we need to show. Okay, so how are we going to do this then? Well, what's the condition for A composed with B to be in the kernel of the homomorphism? Well, that just means that phi of A composed with B would have to equal the identity in G prime, basically. This is what we need to show. So this condition here is absolutely equivalent to this condition, just by the definition of what the kernel of the homomorphism actually is. So we need to show that phi of A composed with B is equal to the identity in G prime. Okay, and now it's just calling out at you what to do, basically. It's screaming out at you what to do. So let's consider this phi of A composed with B. Because we know that phi is a homomorphism, we can split this down now into phi of A composed with phi of B. Now, why is that a fantastic thing to do? Well, we know what the answer to phi of A and phi of B is, because we know that A and B are elements of the kernel of the homomorphism. So what does that mean? That means that phi of A and phi of B are both the same thing. They are the identity in capital G prime. Okay, so now we can just substitute these answers into here, and then we're just composing the identity in G prime with itself, basically. And of course, the identity in G prime composed with the identity in G prime just once again gives us the identity in G prime. Okay, so we've now shown this, and therefore we've shown this. So what I've just shown you then is that if you take any two arbitrary elements, A and B, which are in the kernel of a homomorphism, then the composition of those two elements also has to be within the kernel of a homomorphism, of that homomorphism rather. Okay, so this kernel of the homomorphism has to be closed under composition. So excellent, it obeys axiom number 1 of group theory. As I said, we don't need to worry about axiom number 2, associativity. We can throw that to one side. Okay, we do need to look at axiom number 3, but we've already done axiom number 3. Okay, we need to know that the identity element of the domain group is an element of this subset, the kernel of the homomorphism, but we've already seen that. Okay, the identity element in the domain group is absolutely always mapped onto the identity element in the codomain group. That was one of those theorems that we proved earlier on. Okay, which means that the identity element in the domain group is always an element of the kernel of the homomorphism, so we don't need to worry about that one. Okay, the last one that we need to check out is that there are actually inverse elements in the kernel of the homomorphism. Okay, so what we need to show then is if we take an arbitrary element, let's say little a, which is an element of the kernel of the homomorphism, what we want to show then is that A inverse, which we know is an element of the domain group, okay, because A is an element of the domain group, we know A inverse must exist within the domain group. What we want to show is that A inverse is an element of the kernel of the homomorphism. So once again, I'll just put a to show there. Okay, so that's what we need to show. So we need to show that if you take any arbitrary element, little a, of the kernel of the homomorphism, that its inverse, which we know is somewhere within the domain group, is also in the kernel of the homomorphism. So again, we can reduce this into the fact that we need to show that phi of A inverse is equal to the identity in the codomain group G prime. Okay, this is exactly the same as proving this, basically. But now we can use a fact that we showed earlier. Okay, because we showed earlier that phi of A inverse is the same thing as phi of A's inverse. Okay, it's inverse in the codomain group G prime here. Okay, now we know what phi of A is because A is an element of the kernel of the homomorphism, so phi of A is equal to the identity in G prime. Now what is the inverse of the identity in G prime in this codomain group G prime? Well, the inverse of the identity is always the identity, so that means that this answer has to be the identity in G prime, and therefore we have shown that if A is an element of the kernel of the homomorphism, then A inverse will also be an element of the kernel of a homomorphism. So what we've now shown is that the kernel of a homomorphism is always a subgroup of the domain group, basically, of the homomorphism. Okay, right. Now, what I want to introduce you to now is a new, very, very important concept, okay? And it's the concept of a normal subgroup, because we are going to actually see that the kernel of a homomorphism is a very special subgroup. It's what's called a normal subgroup, but before I can show you that, I firstly need to tell you what a normal subgroup actually is. Okay, so before I can tell you what a normal subgroup is, I need to tell you what it means to conjugate one element of the group by another element of the group. Okay, so firstly a little bit of background. So let's say we've got two elements of the group. Let's say little a and little g, which are elements of some group, capital G, basically. Okay, then when we say we want the A conjugate of the element little g, what that means is A, G, A inverse, like so, basically. Okay, so this is what we mean when we say the conjugate of G by A. Okay, so when people talk about conjugating one element of the group by another element of the group, this is what they mean. The conjugate of G by A, and I'm aware that this is a brand new concept, so we will explore this in a bit more detail. Okay, right. So if someone says conjugate the element G by the element A, what you need to do is you need to take G and then put in front of it the element A, and then put behind it the element A inverse. So to write this out in full, this means A composed with G composed with A inverse, and we know because of associativity that we don't need to put brackets in there. That has only one answer, basically. Okay, so that is what is meant by the conjugate of the element little g by the element little a. So whatever little a and little g you can come up with from our group capital G, you in principle can calculate what this is. Okay, so this is fundamentally just a definition. You might not understand at the moment where the motivation for that definition comes from. You might not understand why you should care, but I hope you can understand that in principle you could work this out for any little a and little g in the group. Okay, right. Now, something to bear in mind is that if G is abelian, okay, so if G is abelian, then no matter what little a and little g you pick, this is totally pointless really. Okay, because if we consider what this is, if the group is abelian, then all elements in an abelian group commute basically. So what we can just do is swap around g and a here. Okay, so because of the commutative composition law, we can swap around the g composed with a inverse with a inverse composed with g. So I can rewrite this as a inverse g, and then of course I can reassociate, I can put the brackets around a and a inverse, and that will then reduce into the identity. So that means that the answer to the conjugate of g by a, or the a conjugate of g, is just g, no matter what little a you pick and what little g you pick. So conjugation has absolutely no effect in an abelian group. This is only an interesting thing to do in a non-abelian group, and it is a really, really interesting thing to do in a non-abelian group, for reasons that we're not going to go into yet in this video. Okay, but it is a really interesting thing to do in a non-abelian group. Okay, right, so that's the definition of the conjugate of one element little g by another element little a, and we've seen that it's completely pointless if you're working in an abelian group. Okay, you just get the element little g back again, no matter what little g you pick and what little a you pick. Okay, now, what then is the definition of a normal subgroup? Well, a normal subgroup is a special type of subgroup, so you need to start off with a subgroup initially. Okay, so let's say we start off with our subgroup capital H, which is a subgroup of capital G. Now, if little h is one of these special types of subgroup called a normal subgroup, then we instead write it like so: little h triangle little g. So this is read, little h is a normal subgroup of capital G basically. Okay, now what does this actually mean then? What is the definition of a normal subgroup? Well, basically it means that this subgroup is stable under conjugation by any element in capital G basically. So what this means is that for all little h is an element of capital H. Okay, and I'll draw a picture here. So let's have our large group capital G here, and then we'll have our subgroup capital H here. Okay, and we're taking an arbitrary little h, which is an element of capital H. So I can take any element I like of my subgroup capital H here, okay, which I'm now supposing is a normal subgroup. This is the definition that it needs to obey if it's going to be a normal subgroup. Okay, so for all little h is an element of capital H, and for all little g is an element of capital G, so you can pick any little g as an element of capital G. Okay, and I'll highlight little g up here in blue. Okay, and it's not necessarily true that little g won't be an element of capital H. After all the elements of capital H are in capital G, so you could pick a little g that was actually in capital H, or you could pick a little g that's outside of capital H. Okay, so for all little h and all little g you could possibly pick. And then if you take the conjugate of the little h by the little g, okay, so if you take gh, g inverse, okay, you conjugate the element h by this element g, okay, which is any element of the group, okay, then whatever this answer is, it has to be an element of the subgroup back again. It has to be within capital H, okay? Right, so that is what we mean by saying that capital H has to be stable under conjugation by any element in capital G. We mean that if you take any element of capital H and conjugate it by any element you choose of capital G, whatever the answer you get, it is an element of capital H back again. You don't end up with an element that's in this portion of capital G that's outside of capital H. You have to get another element back in capital H. So indeed, the subgroup capital H is stable under conjugation by any element from the larger group capital G, i.e. when you conjugate it by any element in capital G, you get another element back in the subgroup basically. If capital H obeys this, then it's called a normal subgroup. Now, just to again give you a trivial example, if capital G is an abelian group, okay, so if the larger group is an abelian group, then of course the subgroup, capital H, will also be an abelian group, okay, and when you consider doing this, okay, when you consider conjugating any element of the subgroup by any element of the larger group, of course, what you get back again, you'll just get little h back again, because capital G is an abelian group. This is all conjugation in capital G, so it will just give me little h back again. So of course, little h is an element of larger h, okay, so this is automatically true. So basically that's a nice trivial example. All subgroups of abelian groups are normal subgroups. Okay, so these are some nice examples of normal subgroups. So all subgroups of abelian groups are normal subgroups. So really this definition only becomes non-trivial in the case of non-abelian groups. Okay, so in the case of non-abelian groups, it is not the case that all subgroups will be normal subgroups. Okay, and indeed, it's not the case that GH, G inverse will equal little h for all little g and little h. So even in the case of a normal subgroup in a non-abelian group, then when you take this conjugate GH, G inverse for some element little h within the normal subgroup, it's not necessary that it will end up as little h, it just has to end up as another element in capital H, so it could end up as a different element in capital H. Okay, so that's an important point to note, that this definition doesn't say that GH, G inverse has to equal little h, it says it has to equal an element in capital H. So it doesn't necessarily take it to the same element as it was originally, it takes it to another element of the subgroup, basically. Okay, right. So as I say, this definition really becomes interesting in the case of non-abelian groups rather than in the case of abelian groups. Okay, so I admit that this definition at the moment seems quite unmotivated, okay? You can understand, hopefully, what the definition actually is, but you probably don't have a clue why you should care at the moment. And I promise you, you will understand how important these are in later videos. Okay, for now, the one thing that I want to show you is that the kernel of a homomorphism actually is a normal subgroup, basically. Okay, so it does satisfy this definition. Okay, right, so what do I then need to show? I need to show, so let's put down what I need to show, and I think I'll try and squeeze it in down here. So let's say we are now dealing with the subgroup, which is the kernel of the homomorphism. So we're saying capital H is now the kernel of some homomorphism. Okay, and we want to show that for all little h is an element of the kernel of the homomorphism, okay, and for all little g is an element of the larger domain group, we want to show that GH, G inverse is also an element of our kernel of the homomorphism. Okay, I've just taken this definition here and substituted in capital H is equal to the kernel of the homomorphism now. Okay, so I need to show that if I conjugate any element of the kernel of the homomorphism by any element of the larger domain group, that I get another element of the kernel of the homomorphism. Well, what do I need to do to show that GH, G inverse is an element of the kernel of the homomorphism? I need to show that phi of GH, G inverse is equal to the identity in capital G prime, basically. That's what I need to show. This is exactly equivalent to this. Okay, so how am I going to do that? Well, I'm just going to split this up with the law of homomorphisms. Okay, the property that homomorphisms obey. Okay, now of course the property that homomorphisms obey is designed for just two elements composed together. I have now got three elements composed together here, but of course what I can just do is bracket this up and turn it into the composition of two elements, and then remove the brackets after I've split it up, and then split that one up into, so it's a split up into three things, and I'll just show you that. Okay, so what I could do if I want to apply the property of homomorphisms to this is I could imagine putting some brackets in. Okay, so I could put brackets around G and H there. Okay, now I can think of this as the two things composed together here. So the answer to what G composed with H is composed with G inverse. Okay, so I could then split it up into phi of GH composed with phi of G inverse, and then I could remember that this is actually two separate things, and then I could apply the law of homomorphisms again to split this up again. So I'd end up producing phi of G composed with phi of H composed with phi of G inverse. Okay, brilliant. Now, what am I going to do with this then? Okay, so the only thing that I know straight away is what phi of little h is equal to. Okay, remember what little h was. Little h was an element of the kernel of the homomorphism. So what does that mean? That it was mapped onto the identity in capital G prime. So I can replace that now with the identity in capital G prime, which means that this becomes phi of G composed with phi of G inverse. Okay, now whatever G is, I know that phi of G inverse like this is equal to the inverse of phi of G. So what I can do is I can replace this with phi of G inverse like so. Okay, and therefore I know that this thing will compose with this thing to give the identity in capital G prime. Okay, so therefore I have proven that phi of GH G inverse like so is in fact equal to the identity of capital G prime for all little h is an element of the kernel of the homomorphism, and for all little g that you arbitrarily pick from the domain group capital G. Okay, and therefore whatever the answer to GH G inverse is, okay, and I don't know what the answer is, unless it's an abelian group, I haven't got a clue basically. It could be any element in the kernel of the homomorphism. All I know is that it is an element of the kernel of the homomorphism because it is mapped onto the identity in the codomain group capital G prime. Okay, so what we have now shown is that indeed the kernel of a homomorphism is stable under conjugation by elements from the larger domain group basically. Okay, so it is a normal subgroup of the domain group. So I might just put this somewhere. So we can turn this thing here into the triangle. The kernel of the homomorphism is a normal subgroup of the domain group capital G basically. Okay, so we will now conclude it there for this video on group homomorphisms. As I say, we will put all of this together in later videos in this playlist on group theory.